So, this course is called Astrophysical Fluid Dynamics. I did ask for a lectern here because I have a problem with my back. It's called Astrophysical Fluid Dynamics. So let me begin by saying that this is a difficult course. It's not an impossible course, but it is difficult. That means you have to work consistently and work hard. So let me start by telling you something about the books that are available. I'm not sure what is in your library, so I've never been able to get access to your library. So I've not had a chance to look at the holdings in the library, but I'll tell you what some very good books are. We can start, first of all, so I'll divide the books into two sections. The first is fluids, and the second is astrophysical fluids. I divide them like this because the books on fluids generally do not address astrophysical problems. They have all the information that you will need on the subject of fluids, but they do not specialize in discussing problems from astrophysics. And the books on astrophysical fluids specifically are set up to address the problems on astrophysics. So under the books on general fluids, I strongly recommend that you look at a book called Eulerian. This is the author's name, and this is called Physical Fluid Dynamics. I'll abbreviate fluid dynamics to FD. The nice thing about Tritton is that he is not too detailed in terms of the mathematical development, but he does give you a lot of insight physically into what the behavior of fluids actually is. Then there is the classic book on fluid dynamics, which is by somebody called Horace Mann. It's called Fluids. The first edition of this book was produced in 1875. So it is an old classic. The last edition was produced in, I think, the 1950s, shortly before Lamb died. It's written in an old mathematical style, and for that reason is not an easy book to read. But if you want to know anything about fluids, the state of fluid dynamics up until the 1940s, say, then this is the book to consult. Because of the way it's written, I sometimes call it the Chamber of Horace. And then there is another classic book which was written by Lamb's successor in the field, and that is Batchelor, George Batchelor. And it's also called Fluids. And that is a fairly comprehensive and modern survey of fluid dynamics. Right, well, the list can be continued endlessly because there are literally thousands of books on fluid dynamics, and what you need to do is go to the library and find one that suits your particular style of learning, and then try to extract the information from it. I will give you fairly full notes. My notes are not in completed form yet, but I am in the process of adding to them, and I shall do that during this course. I did ask the administration to supply me with an email address so that I can let you have a PDF copy of my notes, but I've had no responses yet. If somebody knows to what address I must write to reach all of you, then write it on a piece of paper and let me have it at the end of this session. On astrophysical fluid dynamics, probably the most comprehensive and earliest treatise on the subject is by Frank Schuh. He has two volumes. One is called Gas Dynamics, the other is called Radiative Processes. and the set of 2 volumes is, I think it's called Methods in Astrophysics. But the one that you want is Gas Dynamics. I'm not sure which of the 2 volumes it is. Then there is a book which is specifically written on astrophysical fluids by somebody called Ray Chardry. And I think it's called Astrophysical Fluid Dynamics. A good book, a little bit wordy, and a bit sparse on detail, but otherwise an interesting book to read. There is an interest book by Stephen Shaw, also called Astrophysical Fluids. And this book is a book that you can happily consult after you've learned the subject. He is full of extremely interesting information, and is he doesn't develop the subject from first principles. He just assumes that you know fluid dynamics, and he tells you what astrophysical applications are made of it. And then an extremely good book by Thomson, again called Astrophysical Fluids. This is Mike Thomson. And this is a book that sets up very, very quickly the methods of fluid dynamics, and then applies it. It's devoted to the application to astrophysical fluids. And I suppose somewhere between these 2, I suppose it fits into the gap here. So let me write it like that. Is a wonderful book by somebody called Wallis. I don't know what his initial is. It's a recent book, and this book is called Oceanographic and Atmospheric Fluids. And the first few chapters, obviously the bulk of the book deals with oceans and atmospheres. But the first few chapters of the book deal with general fluids, and it is an excellent introduction to the topic. Right, so that gives you a flavour of what books are available. I have based myself principally on Tritton, Lamb, Batchelor, Shue, and Thomson. So my course is, if you like, a condensation of the material from these books, and fitted together in such a way as to make a 30-lecture course which is fairly comprehensive. All right. Incidentally, feel free to interrupt me if there are things that you don't understand or don't know, or if you want additional explanations. I don't promise to be sympathetic, but I will wear a smile to give you the impression that I am sympathetic. All right, so let's start off with some basic concepts. Maybe I should tell you roughly where this course is going, so that you've got an impression of the content of it. It's a little difficult to crystallize everything, but essentially I will have two strands to the course. The first is on fluids, and the second is on astrophysical applications. Right, so I begin with some general topics on fluids. I suppose you will all remember the early days when you were still in nappies and learning physics, and you started from Halliday and Resnick. Is that right? Is that what you learned physics from? Maybe it was Knight's book, maybe it was Survey, I don't know. Which first year book did you use? Any? Maybe you don't use books. Anyway, you start off with a study of geometry under the heading of vectors. You then study kinematics. Kinematics is the study of how objects move. And so you deal with concepts such as trajectory, velocity, acceleration. You then move to dynamics. Dynamics answers the question, why do objects move in certain ways? And there you studied everything to do with mass dynamics. So you studied momentum, you studied Newton's second law, you studied energy, conservation of energy, conservation of momentum, and all of that basically was the section on dynamics. So I follow roughly the same course, the same pattern that is, because the first thing we need to do is learn how to describe fluid motion. And so my first topic is kinematics. And this is the study of how to describe fluids and the motion of fluids. It doesn't answer the question of why do they move like that. It simply sets out the mathematical formalism by which you're able to describe the movement of fluids. After I've done kinematics, well, I've got some applications here. The first application comes to the study of the motion of the galaxy, and so this is the topic of differential rotation. And the rotation of the galaxy. After I've done the kinematics, I move on to the dynamics. Dynamics consists of a variety of topics, and they include the equations of motion, and the governing principles. So in the topic of the equations of motion, the first thing that I do is I set up for you the formalism by which we can discuss the motion of any fluid. I will specialize that, of course, because there are a lot of different types of situations which require different kinds of approximation, and that means that we must take the equations of motion and apply them to those situations. A lot of people find fluid dynamics extremely confusing, and they find it confusing because there are so many different sets of equations which are set down by different authors in different contexts and for different reasons, and they all look drastically different. So unless you've got some kind of unifying scheme against which to understand all these different equations, it's almost impossible to understand fluid dynamics. It looks like a collection of recipes. But it isn't. Fluid dynamics is built on very sound, basic principles. And the reason there are so many differences in the equations that you find in different authors and different articles is simply because they have taken those basic equations and applied them to different situations, making different approximations and assumptions. So I will set up the general equation of motion, and then I will discuss particular applications of it. I then discuss also the governing principles. The equations of motion are not sufficient to determine the movement of fluids. You'll see why when we get to that section. You need also additional equations, and they are based on fundamental physical principles. The first is the conservation of mass. Then there is the conservation of momentum, the conservation of energy, the conservation of angular momentum. A fluid is also a material substance. It's not solid, that's what makes it fluid, but it is material. And because it's material, it consists of a vast, huge, unimaginably large number of particles. And you couldn't possibly hope to describe the movement of every one of those particles. And so we treat it as you treat anything in thermodynamics. You separate the degrees of freedom that you can track and observe, such as where is its centre of mass? Is it rotating around its centre of mass? But this doesn't describe 10 to the power of 30 particles. You've just described a few degrees of freedom. And so what you need to do is then take into account the other degrees of freedom, and you do that by the principles of thermodynamics. That is, you introduce the concept of internal energy, and you then set up an equation for the material, which is the constant of energy, and you discuss how the energy is absorbed into the material and expelled from the material in different processes. And so we need also some basic thermodynamics among the governing principles. And when you put all these equations together, then you've got a complete description of the fluid and an almost impossible mathematical problem. So you either have to make simplifications to allow you to calculate by hand, or else you go to a computer and a clever computer programmer, and you get him to put the equations into computer code, and you run numerical experiments to see how the fluid behaves. Quite a lot of modern astrophysics is done by means of computers, simply because the systems are so difficult to treat that it is almost impossible to do any calculation by hand. You've got to set up the equations and then run the computer code to see how the system behaves. Alright, so that's dynamics. What I will then do is I will systematically apply these general equations to different situations. The first situation to which I apply it is hydrostatics. That is fluids which are in equilibrium, which are not in motion, and this then allows me to go to some astrophysical applications, and these include plane parallel atmospheres, and also, what else do I do here? I do stellar structure. The principles of stellar structure, of course. Stellar structure is a big topic. And there are one or two other topics as well here, which I won't list because I don't want to spend too long introducing the subject. After I've done hydrostatics, I will then deal with fluids without friction. These are called ideal fluids. And this is where the complications begin, because now you've got lots of different ways to classify the systems that you're describing. So let me give you just some classifications. From ideal fluids, we can talk about compressible fluids and incompressible. Incompressible fluids are the easier ones to deal with mathematically, and they usually are the ones that are dealt with in books on fluid dynamics. Most of the fluids that we encounter in astrophysics are compressible, and therefore it makes it a little bit more difficult as a subject. And the application of compressible fluids is to jets. And we will see how to make gases move supersonically, and maybe give an elementary example of jets either from a star or from a galaxy. And then, under incompressible, you have two types of motion. They are called, I don't think I can reach at the top chord, they are called irrotational and rotational. I will explain what these words mean when I get to it. And you've got exactly the same division under incompressible fluids. And these four divisions will repeat under every other topic that I can list from here onwards. So let me bring this brief summary to a close by saying that we then deal with fluids with friction. These are non-ideal fluids called viscous fluids. And the application to astrophysics for viscous fluids is in accretion disks. Right, so that should give you a broad outline of roughly what the course entails. As you can see, there is a huge amount of material to be covered here, and I can't possibly even begin to imagine that I might do it justice. But this is an introduction, and what I will do is attempt to give you a flavour for the vast number of things that can be described in fluid dynamics and just how interesting these systems are. Right, do you have any questions before we continue? Yes.
Just the structure of the lecture timetable, I noticed there's 3 lectures a day. Is there any particular...
No, there shouldn't be 3 lectures a day. There are 2 lectures in the morning, and I asked for 2 afternoon sessions per week to be reserved for tutorials. Clearly we can't do any tutorials until we've got a sufficient amount of material. So maybe on Wednesday, if there is a sufficient amount of material, we can start on the 1st, otherwise it will have to be Friday. But this is a lecture course of approximately 30 lectures, I was told. And so the lecture sessions are in the mornings for the next 3 weeks. 10 lectures a week. Any other questions? Right, so then let's begin with some basic concepts. What is a fluid? Let's hear what impressions you have of a fluid. Can you tell me what a fluid is? And what are its characteristic properties? So this thing over here, is this a fluid? No. Why not?
That's a fixed shape.
Hmm?
It has a fixed shape.
It has a fixed shape, yes. It has what we call rigidity. You may be able, by the application of sufficiently strong forces, assuming that it doesn't slide across the floor, you may be able very, very slightly to distort it. But you won't be able to distort it very much. And if you apply forces that are too large, the forces will break the molecular structure and cause either damage in the form of fractures, or else it will make the material break apart. So it is rigidly bound. The molecules are rigidly bound. What about the glass over there? Is that a fluid? Is it a solid? What is it?
Solid.
Solid?
Yeah.
Yes, now that's a difficult one. It's a difficult one because if you go to Europe and look at buildings that are 1,000 years old, you will find that the glass has moved downwards, leaving a thin portion at the top and a thick portion at the bottom. So it's not exactly solid. It's solid over periods of decades, right?
Condensed fluid.
Condensed?
Fluid.
Condensed fluid,
Yeah.
meaning?
There's a fluid that is actually meant to be compacted.
Okay. So what would you understand? Can you give me an example of a condensed fluid?
Like Pyrex or something.
Pyrex. Yes. Pyrex. So it's glass. Yes. So it's a bit like that one over there. The difference between Pyrex and that glass is that if you put that glass into the alum, it cracks. Pyrex doesn't. But basically it's glass. So what I'm trying to tell you is that sometimes over a sufficiently short period of time, something may behave like a solid. You can fracture that glass just by hitting it. Or if you leave it for a sufficiently long period of time, under the action of forces, it begins actually to move and to flow. And there is a transition between fluids. So let me tell you basically what a fluid is. A fluid is something which has got cohesion. That means there are intermolecular forces which pull the material together, but the cohesive forces are not sufficiently strong to resist movement, resist any force that you apply that tries to force these particles apart. So a fluid, in fact here is your definition of a fluid, is any substance incapable of resisting applied shearing forces. Shearing forces are forces which are applied tangentially to the surface. So if you shear something, you apply forces top and bottom to it that push in opposite directions. So a fluid is anything that is unable to resist shearing forces. If you push a fluid at the top, the fluid will begin to move, and it will continue to move as long as you apply a force to the top surface of that fluid. So a fluid may be able to resist compressive forces. If you apply forces in all directions towards some center, the fluid may be able to resist. If it's a liquid, if it's a gas, it will compress. It won't resist even normal forces. Liquids resist normal forces and do not compress, at least not significantly, under the action of perpendicular forces. However, liquids and gases together are not able to resist applied tangential forces or shearing forces. And that is what makes a liquid a liquid. A solid does respond very slightly to tangential forces that you apply to shearing forces. It responds by shifting very slightly and then resisting. So an example that might be familiar to you is you take a block of, say, elastic material and you push the top and the bottom tangentially. The elastic will deform, but then it will come into a new equilibrium and you won't be able to move it further without either increasing the force or damaging the material. Right, so fluids are both solid, liquids and gases. What is the difference between a liquid and a gas? Actually, that's too difficult a question. It requires too many qualifications. Let me ask you something different. Okay, what are the characteristic properties of liquids and the characteristic properties of gases which are different from each other? Yes?
The separation of the molecules that make up the gas. In the gas, they are a bit wider compared to the liquid.
Yes. So in a gas, you're talking about the intermolecular forces. In a gas, the intermolecular forces are generally almost negligible, if not completely negligible. In a liquid, the intermolecular forces are much stronger, and so the material is pulled together much more efficiently. This has a result in density. The density of a liquid is almost constant. When I say almost constant, I mean that if you fix the temperature and the pressure, then the density is fixed in the case of liquid, and it doesn't change. It has a fixed value. It may change very slightly if you change the temperature. If you change the temperature, the liquid might expand so that the same mass fills a slightly larger volume, and so it becomes less dense, but almost constant density. A gas, on the other hand, does not have any fixed density. Or we model it as an incompressible fluid, whereas the gas is compressible. Right, so now that we know something about the nature of the liquid, let me tell you that there are two different ways, as always, to model the fluid, whether it's liquid or gas, as there are always two ways to model any material. The first is macroscopically, and macroscopic means from a large point of view. We're not interested in asking questions or answering questions such as, what is the ultimate constitution of matter? Is matter atomic or is it not atomic? The macroscopic approach to the subject of fluids does not ask that question. In fact, it is not even interested if there are any atoms or molecules in the small scale. All we want are the gross properties of the material that you can measure in a laboratory, things that you can see with your eyes, if you like. You can always model any material system, whether it is a fluid, liquid or gas, or a solid. You can always model it macroscopically without asking questions about the way that the material is made up. The other approach is to produce a microscopic model. In the microscopic approach, what you do is you consider the material as made up of individual atoms or molecules or particles. And then you try to set up some equations which model the fluid from that point of view. Obviously, any decent amount of fluid will have a vast number of particles, and so you can't produce equations. I mean, you can produce equations, but you will never be able to solve the equations because there are too many of them. You don't want to solve 10 to the power of 30 times 3 equations, differential equations of second order, coupled. And so you have to find some different approach. And that different approach is to apply the methods of statistics to work out the average properties of these systems. The approach that I will take in this course exclusively is the macroscopic approach. I will treat the material as if it is matter which is continuously distributed in space, and I'm not interested in whether, if you go sufficiently small, to sufficiently small distances, whether this matter becomes atomic or remains continuous. So that is the approach that I will take. It's a macroscopic approach, and what this means is that we must model the material as a continuum. So, macroscopic model. The material is assumed to be a continuum. Now, what do I mean by a continuum? What I mean is that we assume that the material is distributed right through space. Space, if you have material filling a portion of space, such as this volume occupied by this desk, then we assume that there are no holes, there are no gaps, there are no spaces between different parts of the material that make up this unit. Right? So if we imagine that every point in a certain region of space is occupied by material, and there are no points which are not occupied by material. Of course, we know that isn't the case. But to very good approximation, if I'm interested in an object the size of this table here, then the approximation is pretty good. Only when you start to probe at very, very small distances, 10 to the minus 8 meters, for example, then when you begin to detect atomic properties of the material. As far as we're concerned, at the macroscopic level, we assume the material is distributed through space in such a way that any region occupied by the material There are no holes in that region. Every point has material at that point, and there is no point where there is no material inside that volume. That's what I mean by a continuum. All right, so what we're going to do is set up a way of describing the material in the continuum. The first thing that I'm going to say to you is perfectly self-evident to you because you have done this in your elementary physics. When you deal with a continuum model, any volume of space it contains the material, and this is any volume no matter how small. Maybe I shouldn't use a word like matter in a sentence here. Irrespective of how small. That volume might be. And so this allows us to consider a position in space. I'm going to call my position x, vector x, and vector x is an abbreviation for the 3 coordinates that you're going to use. Whatever coordinate system you choose, I will start always with Cartesian coordinates, but it is more convenient in some of these topics that I've listed to deal with spherical or cylindrical coordinates. Whatever coordinate system you use, you give me the set of 3 coordinates that identifies the position. The position I will mark as position x. That is x with a vector over it. So what you do is you take a small volume, which I will call delta V, and no matter how small the volume is, delta V will contain, suppose delta V contains mass of the fluid, delta M, then what I do is I define the density at position x at time t to be the limit at time t as the volume is made progressively smaller around this point, but always containing it, of delta M over delta V. And as I make the volume smaller and smaller, of course I will get a smaller and smaller mass, but this fraction will tend to a definite limit. At least the assumption of the continuum model is that this quantity, this ratio, tends to a limit, and that limit is what we call density. And we use this formula by saying, when we consider small elements of fluid, we will use this formula to calculate the mass of the element approximately from the formula rho at x and t times the size of the volume that we're considering, which is occupied by that. Now obviously if you have atomic material, this is a nonsense statement, because if I take a large volume, it will contain material. The smaller half the volume, it will contain material. Still half the volume, it will contain material. But eventually I will get to a size of the volume where it either contains exactly 1 atom or no atoms. And so in an atomic theory, this ratio does not exist. In a continuum theory, it does, because you assume that no matter how small you make the volume, you always have some mass contained in it. All right, that's one of the first items that we need for the description of the fluid. What times are your lectures? 8 o'clock and 9 o'clock, are they? Is that right? And then we finish at what time? 10. Quarter to 10. Right. So let me tell you 1 or 2 other things, and then we can have a break and continue with the second lecture. Right, so the thing about fluids is that they move. fluids move. That means I need to describe how they move. So this now puts me into a slight predicament because I need to introduce some terminology to you. The first thing that I want to introduce to you, okay, so let's do a thought experiment. Suppose I take a volume such as that box over there. How many points are contained in that volume? How many? Infinite. Infinite number of points. Yes. It's worse than that. It's infinity cubed. Because I have an infinite number of choices for the x-coordinate, an infinite number for the y-coordinate, an infinite number for the z-coordinate, so there are infinity cubed points in there. Right? So the situation is that. How much mass is contained in this box?
Density of mass.
Hmm?
You multiply the density by the volume.
Yes, multiply the density by the volume, that's true. What I wanted you to say, had you read my mind, is that the mass is finite. So, what is the mass of a single point in this box? Finite number, yes? Zero, exactly. So when you are dealing with a continuum theory, you cannot assign a mass to a point, right? Points have no mass. In order to have a mass, you need a finite volume. No matter how small or how large it is, you need a number of points. In other words, an infinite number of points, because any small volume contains an infinite number of points. And this means that I need to distinguish two things. The first is a fluid point, and this is a single point in the fluid whose motion we follow. If you could imagine painting a point, in order to follow the motion of that point, what you do is you paint that point red or blue or whatever your favorite color is, and you watch it in the fluid as it moves. Right? So what I will mean when I say a fluid point, I mean a single point in the continuum whose motion we will follow as the material moves. And then I will talk about a fluid element. A fluid element is a finite volume of fluid points, which means an infinite number of fluid points, and the finite volume can be of any size. Usually, if I say a finite fluid element, I mean of any size that you want. And when I say a fluid element without any quantification, I will mean a sufficiently small volume so that we can regard it as sufficient of infinitesimal size, but it still consists of an infinite number of fluid points. Okay, well, that's probably a good place to stop. I will tell you after we've had a break, 10 minutes. My watch now says 10 to 9. So we will recommence at 9, and I will then describe to you how we set up a description of the motion of this continuum of fluid points. Fluid velocity, I've distinguished the fluid point from the fluid element. I will try to be consistent with way that I use these terms. When I say fluid point, I mean a single point in the fluid whose motion we're going to follow. And when I talk about a fluid element, I will mean some small volume of fluid, or maybe sometimes even a large volume of fluid, whose motion we follow every point of the element will be followed. Right, so how do we describe the motion of the fluid? Well, there are two different approaches which are generally followed in fluid dynamics. Clearly, every fluid point has got a trajectory, and one could begin from the trajectories of the fluid points, then define the velocity of the fluid points and the acceleration of the fluid points. This leads to what is called the Lagrangian description of fluids. On the other hand, what you could do is focus your attention on particular volumes of space and ask, what are the properties of the fluid in that volume of space? And this is generally called the Eulerian approach to fluid dynamics. I don't know why people call the one Lagrangian and the other Eulerian. Both were invented by Leonhard Euler, and he used both, and Lagrange was his junior, and Lagrange developed the fluid dynamics whose foundations Euler had written down. But anyway, that is the terminology that is used. Let me introduce to you what the so-called Eulerian velocity field is. So, what we do is consider the fluid at position x at time t. The fluid point has a velocity, and that velocity is denoted by v at x at time t. So essentially what we have, of course, at a given time t, the fluid will occupy a very large number of positions. The fluid will occupy a domain of positions in space. And so for every position in the region of space occupied by the fluid at this time t, every fluid point has a velocity. So essentially what we have here is a function, v, into whose arguments you put the position of interest and the time of interest, and the function returns to you the value of the velocity of the fluid point at this position and time. In other words, v is a vector field. For every position and every time, you get a value of v, which is the value of the velocity of the fluid point, which is at position x, and at time t. This is an important concept, and it's a different concept from the concept of the velocity of a point particle. It's different because this is a vector field, and we will have to take into account the fact that it is a vector field and the meaning of the vector field when we calculate the acceleration. Right, there are a number of things that we can discuss from this concept of the velocity field. And these things, I will list them for you. I will then discuss two of the three and leave you as an exercise to work out the third. So from the velocity field, we introduce three concepts. The first is that of a streamline. The second is that of a pathline. And the third, which I will leave you to work out from my notes, is that of a street line. So let me tell you what I mean by these three concepts. A streamline, first of all. What you do is you take a photograph of the fluid at fixed time t. Streamline. What you do is you consider the fluid at fixed time t. So t could be 0, it could be 1 second, it could be 10 million seconds. It doesn't matter what the value of t is. What you do is you fix the value of t, and conceptually that means you photograph the fluid at a certain fixed time. So the time t is fixed. And what you then look at is the set of velocity vectors. Consider the velocity vectors at each time t. I'm sorry, at each position x at the given time t. So here is a picture, a silly picture. I'm not terribly good at art, I'm proud of it. I'm a scientist, I'm not wishy-washy and arty. So, at every point you can draw a velocity vector. The different fluids, the different fluid points will have velocities in different directions and of different sizes. And what we now do is we look for curves such that the velocity is tangent to the curves at every one of its points. And these curves are called the streamlines. Now this concept is familiar to you from your elementary study of electricity and magnetism. In electrostatics, you introduced the electric field lines. In magnetism, you introduced the magnetic field lines. And this is precisely how the field lines were defined. What you do is you draw curves which everywhere are tangent to the vector field, whatever the vector field is. In the case of electrostatics, it's the electric field. In the case of magnetism, it is the magnetic field. Now we do exactly the same thing in fluids, and in the case of fluids, we call this the streamline. What it does is it gives you a picture of what the motion of the fluid looks like at this instant t. It doesn't tell you how individual fluid points move. It simply tells you what the vector field looks like at that given time t. And so these lines give a picture of fluid velocity at time t. I emphasize, it doesn't tell you how the fluid moves. It shows you what the velocity field looks like at this instant. All right, so let's do some elementary mathematics now. So, denote the equations for a curve, and I'm using Cartesian coordinates. So how do we describe a curve in space? Any ideas? First year physics. Probably first year mathematics as well. Any ideas? No? Have a guess.
Assigning a function for every vector.
A function for every vector, so
No, I mean surface. Surface.
surface.
Yeah.
Surface. Now how does surface describe a curve?
Actually, a surface might be a bunch of curves.
It could be a bunch of curves, yes. That's right. We're getting a bit closer.
Yeah, something like assigning something like parameter.
Parameter?
Yes, certain parameter for
Yes, very good. So what must be parameterized?
lambda something.
Yes. Well, you can call it Fred or Charlie. Doesn't really matter what you call it. Lambda, let's call it lambda. And then, what do you do with this parameter lambda?
Okay, call something like surface number 1 equal function of lambda and t, something like
Yes, but this will give you a family of surfaces.
that. Yeah.
And the surface you already told me is a family of curves. So I want just one of those curves. Alright, so let me put you out of your misery. What you want is something, we're going to work with a parameterized curve. So we will have a parameter lambda, and for every value of lambda, you want 3 functions that return for you the position of the point that sits at that parameter value. So we have a curve here. Lambda is equal to 1 here. Lambda is equal to 2 here. Lambda is equal to 3 there, maybe. And so on. Lambda is equal to 0 somewhere here. Lambda is equal to -1 here. And so on. That will describe a curve. So what am I describing in ordinary everyday terms? Alright, so you've got a railway, you want to catch a train. In order to catch the train, you need to know where is the railway, first of all, and secondly, at what time does the train pass each of the points on that railway. Right? So here's the railway. Here are, if you like, the times at which the train arrives at different points. And this is what we're trying to describe. This is the trajectory. The trajectory from your first year mechanics, isn't it? And so what I want is x given to me as a function of lambda, y as a function of lambda, z as a function of lambda. Give me a value of lambda. These are given functions. Are you happy with the fact that I'm abusing notation by using the same symbol to describe the function as I use for describing the output? Standard mathematical abuse of notation. It's also called the principle of the conservation of symbols, because we only have 26 lowercase letters in the English alphabet, 26 uppercase letters, and you will soon run out of symbols. So, in fact, we do. So we ransack the Greek alphabet as well, and there we have 22 lowercase symbols and 22 uppercase symbols, but 22 uppercase symbols, many of them look exactly like the English alphabet, so we don't add more than 22 symbols. And the ones that don't look like the English are so difficult to write out that we don't. So basically we've got 26 plus 26, how much is that? 52 plus 22, that's 54, 74. We've got 74 symbols available to us. So unless you want to go to the Cyrillic alphabet, and the Arabic alphabet, and the Chinese alphabet, and the Japanese alphabet, and the Russian alphabet, and the Hebrew alphabet, and Sanskrit, you will soon run out of symbols. So we conserve symbols, by abusing notation. The abuse of notation is acceptable for as long as there is no ambiguity. So here, the function x next to the bracket, the x next to the bracket means a function, and the x on the other side of the equal sign means the output of that function. They're not to be confused, right? Because they're different things. You don't have calculators with you. The calculator is the function. It sits there, quietly, waiting for an input. As soon as you put the input into the calculator and press return, it grinds away. They don't anymore now, they electronic away, and they produce an answer which is flashed on the display. That's the difference between this x and that x. Alright, and these three functions, again, this time it is not the principle of the conservation of symbols, it is the principle of the conservation of chalk. And what I will do is I will abbreviate these as xi is equal to xi of lambda, where what I've done what the Romans do. You know, in the old days, in order to make your family survive, you had 10 children or 12 children, most of them died before they were 3 or 4, right? And the Romans ran out of names. So what they did was they called them primus, secundus, tertius, quartus, quintus. In other words, they gave them numbers. That's what we've done here. We've called x, x1. We've called y, x2. We've called z, x3. Roman style, and then the symbol I goes from 1 to 3. And when I write the symbol xi, I mean there is one such statement for every possible value of I. You're familiar with this, you've done tensors, haven't you? Yeah. You're doing this in GR, I take it. So you're familiar with the index notation. Alright, so this is a shorthand for these three equations. And I need to admit it requires less chalk, and therefore it is the principle of the conservation of chalk. How do I calculate? So these equations describe the curve. They are the equations for a trajectory. I haven't called the parameter t because I don't want to confuse the parameter of the curve with time. So we've called it lambda. But it is basically a curve, a trajectory in space. How do I calculate the tangent to the curve? Say, at a given parameter value lambda. Here is the vector that is tangent to the curve. How do I calculate the tangent vector?
It's a first derivative.
First derivative. Thank you. So the tangent vector to xi of lambda at position given by parameter value lambda has components dxi by d lambda evaluated at lambda. Please note that I put in the arguments. When I put in the arguments, it is for a specific reason. I'm not just being stubborn or pedantic or difficult. It is for a specific reason, which you will see in a moment. And it is always, there are certain situations where you need to put in the values of the function, the arguments of the function, when you write out the statement. Sometimes you can omit it without any ambiguity, but sometimes it is important to put it in for the sake of clarity. Alright, so these are the components of the tangent vector. I now want, according to the definition, where was it here? I am looking for a curve whose tangent vector at any position is given to me by the velocity of the fluid point at that same position. Right? So we want dxi by d lambda and lambda to coincide with the velocity of the fluid at that position. And it is at the fixed time t. Right, so what is the velocity of the fluid at position given to me by the point on the curve corresponding to parameter value lambda? The velocity field was defined somewhere over here. It's been worked out. So what do I need to do with the velocity field to calculate the velocity of the fluid at this position at this time? I need to substitute the coordinates of the position of interest. Do I not? Right. And so the velocity of the fluid, so at position xi of lambda, the fluid has velocity v at x of lambda and the time t of interest. Because I'm looking at position x of lambda, it's the position on the curve. I want the velocity at that position, so I put the coordinates of that position into the velocity field. And so, to have the fluid velocity equal to the tangent to the curve at parameter value lambda, what I must have is dxi by dt. Dxi by d lambda, beg your pardon, at position lambda is equal to the ith component of the velocity at position lambda at time t. And this must be true at every position of the curve so what do I have on the left-hand side? What kind of function is it? Of what variable is it a function? Lambda. On the right-hand side? It's a function of lambda. Actually, it's a function of lambda, but it's a function of lambda. T is a fixed value, so it's a number. I've substituted a number in place of t. So here I have a statement which is, I've got a function of lambda is equal to a function of lambda. This equality must hold for all possible lambda, and this is called an identity. Any equality that holds for all possible values of a variable is called an identity. I.e., we have an identity in lambda. Right, now, some of you I can see your faces are looking a little bit nonplussed, and don't be nonplussed. You know, science is science. Science must not make mistakes. Science is accurate. It isn't sociology or politics or psychology where you make it up as you go along. Right? Science is science. It is perfectly precise and perfectly accurate. So if you're going to make any progress in science, you must be precise. So don't look disturbed by the fact that I'm being very precise. The second thing I must tell you is what Galileo told his students, and it is this: nature is written in a language. It is written in the language of mathematics. If you want to understand nature, you must understand the language that nature speaks, and that is the language of mathematics. So don't be perturbed by the fact that I'm giving you information about mathematics. You will never understand nature unless you understand mathematics. Don't think that I'm trying to turn you into a mathematician. A mathematician is a very poor form of astrophysicist. It's true. It's a poor form of astrophysicist simply for the following reason. Mathematics is form without content. Physics is form and content. The mathematician is only interested in the form of the argument. He's not interested in the content of it. Physics, on the other hand, must have the form of the argument, and it must infuse the symbols with physical significance. So we have a dictionary that tells us what the symbols mean. To what do they correspond in nature? The mathematician doesn't do that. So physics is like doing a jigsaw puzzle on which there is a picture. You fit the pieces together, and you've got the picture to guide you as to which piece goes where. Mathematics is doing a jigsaw puzzle without the picture. They just look for the pieces that fit, and they have no idea why they're looking for it. All right, so we have an identity in lambda. Let me ask you now the definition of a solution of a differential equation. What is a solution of a differential equation? Anyone? You groaned at the back there. Was that the beginnings of an answer?
No, I was just trying to compare them according to their orders, because the first order gives you the tangent, second order, if you do in the second order differential equation, then give you something like either acceleration, something like that. So trying to bring them back. So.
Right. But you're interpreting the equation. I want a straight definition of what we mean by a solution of a differential equation. Anyone? No? All right, let me tell you that. The solution of a differential equation is a function which, when substituted into the differential equation, what do you mean by satisfy?
I don't know.
Don't tell that to your girlfriend.
What's the word they say is like it makes the right hand side equal, the left hand side equal.
Yes, yes, that's exactly what I want. It makes the left-hand side equal to the right-hand side for every value of the independent variable, or if it's a partial differential equation of the independent variables. In other words, when you substitute the function into the equation, you get an identity in the independent variables, right? So now I turn this equation, this statement, this definition around, and say I've got an identity in the independent variables. There is therefore a differential equation to which these functions are solutions, these functions of the curves that I am searching for. So I have been able, from an identity, to extract a differential equation that must be solved to deliver to me these streamlines. All right, so we have an identity in lambda, i.e. xi of lambda are solutions of the differential equations. In this case, there ordinary differential equations, dxi by b lambda is equal to vi of x and t, and this is where v are given functions and t is a given value. Alright, so basically what I need to do is solve this set of differential equations. Now I was searching in my notes previously to see if I have an example, but I seem to have omitted it from my notes. I will insert it in the next version of the notes. And let me try to devise an example for you now. So a fluid has velocity field V is equal to T y x hat. Everybody's familiar with what I mean by x hat? Maybe you call it I, j, and k. I call them x hat, y hat, z hat. It's the unit vectors for the Cartesian system of coordinates. Find the streamlines. We'll streamline through the point 1, 0, 3. And streamline through this point. Stop. So here is my Cartesian system of axes. Here is x, y, and z. I have a velocity field. Now at position 1 and 3. Oh, at time, that's what I was searching for. At time t is equal to 2. And I take a photograph of the fluid at time t is equal to 2, and passing through the given point is a curve, which is the streamline of the fluid. I don't know what the curve looks like at this stage, I have to work it out. But that's essentially what I have. I photograph at time t is equal to 2, and I'm looking for a curve which is everywhere tangent to the velocity field at this time, and through every point in space there is such a curve. I'm looking for the curve that passes through this particular point. Everybody happy with it? You understand the problem? Right, so how do I set this up? What is my first step?
Sorry, just solve the simple differential equation, dx by dt equal to yx.
Okay. Right, so let me break it down in steps for you. That's absolutely correct. Step 1. Find v at time t is equal to 2. And that means v. I substitute the value t is equal to 2 there, so this is 2y x hat. And what this means is that the first component, v1 of v, is equal to 2y. The second component is equal to 0. The third component is equal to 0 because there is a 0 coefficient to y hat and a 0 coefficient to z hat. step 1. Step 2 is to set up the differential equations. This is set up the differential equations that define the streamline, and they are dx by d lambda is equal to v1, this is dx1 by d lambda is equal to v1, dx2 by d lambda is equal to v2, dx3 by d lambda is equal to v3. v1 is 2y, v2 is 2y is 2x2, and v2 is 0, v3 is 0. So I have a set of coupled differential equations. The second two, yes?
A bit lost. How did you get that V1, V2, and V3? I see how you got the
From here.
I see how you got the V substituted to that equation of the original one.
Yes.
Substituted with V.
Right. So V is equal to V1 x hat plus V2 y hat plus V3 z hat. That's my general expression for V. And I compare it with what I've got, which is over here. And so I've got 0 times y hat plus 0 times z hat. There is no y hat and z hat, and so the coefficients must be 0. And V1 is the coefficient of x hat, which is 2y. Happy? And y is x2. So you write this here, 2, x2. You can work in terms of x, y, z, or x1, x2, x3, it doesn't really make any difference. These two are very easy to solve. And because I can solve equation 2 easily, then I've got x2 to substitute into the first equation, and then that becomes a very easy equation to solve. Right? And when you solve differential equations, you must always have either initial conditions or boundary conditions. If it's partial differential equations, the boundary conditions tell you what happens at the boundaries in space, the initial conditions tell you what happens at a certain reference time. Here we have ordinary differential equations. I need initial conditions, and the initial conditions, the ICs, are given to me by the data of the problem, which is somewhere up here. So it says find the streamline through that point. That means that lambda is equal to 0. I want to be at that position. So the initial conditions are that x1 at lambda is equal to 0 must be 1. x2 at lambda is equal to 0 must be 0. And x3 at lambda is equal to 0 must be 3. The initial conditions, and I can now work out the solutions. So, let me call these equations 1, 2, and 3. Equation 2 tells me that x2 is equal to a constant. Let me call it C2. x3, equation 3, tells me that x3 is equal to constant C3. And equation 1 then tells me that dx1 by d lambda, which is equal to 2x2, that means 2c2, And that means then when I integrate, I get x1 is equal to 2c2 times lambda plus c1. I can now put in the initial conditions. So x1 is equal to 1 when lambda is equal to 0. And this means, therefore, that if I take the solution for x1, put 1 for x1, and I put 0 for lambda, this gives me c1. So c1 is equal to 1. My second initial condition is that x2 is equal to 0 when lambda is equal to 0. And so I take the equation for x2, here it is, and I put x2 is equal to 0. When lambda is equal to 0, lambda doesn't appear on the right-hand side, so I've got nothing to get rid of, and I'm left simply with c2. So c2 is equal to 0, and similarly x3 is equal to 3, is it?
Yes.
When lambda is equal to 0, and what that means is that x3, where is x3? x3, 3 is equal to c3. I've now evaluated the three constants of integration, and so the equations of the streamline streamline are now x1 is equal to 2c2, which is 0, plus c1, which is 1. X2 is equal to c2, which is 0, and x3 is 3. Strange, isn't it? What's strange about it?
The same point.
Same point.
Yeah.
In other words, the fluid at that position is stationary. Doesn't move. Have I made a mistake? I don't think so. I think I've done it correctly. So I made up the example on the spur of the moment. I chose the initial conditions badly. What I should have done is asked you to find the streamline through a different position, say 1, 1, 3. Let me do that. Streamline through 1, 1, 3.
But sorry, sir, before we go to what is the significance of that answer? Are you saying that the fluid is not moving?
The fluid at that position is stationary.
So what does that mean?
It means you've got a stagnant point in the fluid. The fluid around it is moving, but the fluid at that position is stationary.
Okay.
No, it happens. You know, if you sit in your bathtub and you do this in the water goes around you and the center point stays still. And it's perfectly possible for a single point, or if you go to where you see a river, and in some places in the river you find leaves that fall into the surface of the river and they stay there. That means the fluid is not moving there, even though around it the fluid is moving. So we've discovered a stagnant point. This is an accident, a bad choice of example. So let me quickly do at position. So this is the streamline through position 1, 1, 3, and then you will find that the only thing that changes is exactly the same calculation until I get to the initial conditions, and then I will have 1 is equal to C2, and what that means then is that x1 will then be equal to 2 lambda plus C1, and C1 was 1. So if you go to a different point nearby, the fluid is moving. What kind of curve is this one? x1 is equal to 2 lambda plus 1, x2 is equal to, in this case, it is C2, which is 1, and x3 is equal to 3. What kind of curve is this? It is a line. It's a line where x1 changes, x2 does not, x3 does not, and so at that position, so we are now at x1, it's the point 1, 1, 3, so it is 1, 1, 3. Through this point, you have the fluid moving parallel to the x-axis, and it is moving. In fact, you will find that all of the fluid points on the zx plane are stationary. All of the points away from the xz plane are moving in a straight line with different velocities. You can put in different values of the initial condition and see for yourself. All right, do you have any questions? Shall we call it a day? Please work through this material, make sure that you understand it. I will send you an example, or 2 examples maybe, to do on streamlines, and make sure that you do them so that you understand what we are constructing. It's important that you keep on top of your work right from the beginning, because this is a very intensive course. You have 10 lectures a week, 2 lectures a day. If you don't keep up, soon it will sound to you as if I'm talking to you in Chinese.